live demo, live coding. One of the reasons I asked is there's a very similar session to what I presented in Spring 1. We kind of want to talk the same, maybe with a little bit more context. Let's make this as open as possible. So you guys want to drop me with your questions early. I have no problem with that. Let's make it a conversational thing. So first off, thanks for having us. And Fred Melo, we're going to be talking about data microservices and what we call a cloud-native enterprise integration patterns. We're proud to call Spring Call Data Flow. Anyone heard about that before? A few people, okay. And let me see how many of you already use Spring actively. Okay. Heard about or used Cloud Foundry, the platform? Okay. Well, we'll be talking about all that. So stop me if you have any questions, and we'll discuss it. So again, live in the Bay Area. This is my Twitter handle. If you want to keep in touch, want to be friends on Microsoft, LinkedIn, here it is. And let's start with a simple base level, right? We are pivotal. We are focusing mostly on transforming the way people build software. We're basically focusing on helping people deliver software easier, faster, and for that we built a company that has both assets and services that will actually help enterprise get there. And this is the way we engage with companies from different industries. That's the way we engage, for example, with Ford for just building their new connected car. That's the way we involve with engaging with insurance companies, with medical device companies. We actually have some cases there, with car manufacturers, with banks, with telcos, etc., etc. So in the industry, we're coming from this time that people have been for the last 2 decades coming from waterfall methodologies, where they actually have been building those huge monolithic applications that takes sometimes dozens or hundreds of developers together to build a simple and unique piece of software that can actually realize their business needs. We all know that one of the problems with waterfall is actually when you finally get it done, the requirements all changed. It's really hard to make any changes. And most important than that, it's really hard to iterate on and deliver software faster. What the industry have been basically moving towards, from a process point of view, is actually be able to ship software consistently faster with much smaller release cycles that carry much less risk individually because they have small deltas. And that means your risk in general is smaller, you deliver software faster. And that's the whole thing about adopting agile and growing continuous delivery, etc., 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 right? But we also learned that if we want to adopt that, we need to stop getting that huge development team and building one application that we've been calling it monolith that has all those business concerns inside. So if you imagine we can have a single application in the exact example that has order management, user management, inventory, payment, shipping, etc., 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 as a single deployment unit that has a few issues with that. First, when you finally can coordinate everyone to build the exact same thing and ship it, every little change you make, you're going to impact everyone else's work, of course. Second, specific pieces of software have different scalability needs. That means that maybe your front office, if you imagine this as web store, a front office that actually handling all the order management usually needs much better scalability needs than the back office that, for example, handles all the shipping, because maybe you can actually consolidate all the shipping at the exact same time. You don't need to scale immediately to the user's needs as much. Different pieces of software also have different, not only scalability, but availability needs. So what you really want is actually to build small pieces of software that can be developed independently by small teams that can ship their features faster without affecting each others, and then we route this small piece of software on a very clear contract, and then you have microservices, right? And then we learned that if we start to decompose components into small pieces of software that can be delivered independently, then we became much faster to deliver software. Anyone heard how frequent Netflix delivers software today? How many times deployed per day? Many people heard rumors about it.
Hundreds?
Last time we chatted with them over Spring One, they're actually delivering software in general at 86 seconds. So they have thousands and thousands of microservices, and they're adding, changing, fixing features in one of those microservices all the time, all the time. A lot of teams in parallel deliver new features all the time, without any downtime, blue-green deployments. I deliver a new feature for a specific 10% of my users, for example. As it works out, I keep training all the old versions to the new one. You deliver software incrementally. You make sure everything works well. We employ practice like secret breakers, for example, for making sure all dependencies are met. So it's really interesting. And actually, Pivotal has a really interesting work with Netflix on taking all the components that manage those microservices to put in the Cloud Foundry platform. Try to build one of those Spring Cloud Services, Netflix OSS. So we open source those components together into a Spring ecosystem that actually work. But as we actually start building those microservices, you get to a point that's where most of Cloud Foundry users are at this point. They're going to just build a small piece of software that we call a microservice. You code it and make it ready, and basically you just push it to the cloud. If you've never seen Cloud Foundry working, it will basically take your piece of code, understand what's inside it. So it might look and say, oh, it's a jar file. Oh, okay, it looks like Java. And it opens a jar file, sees a bunch of classes and say, it's definitely a jar file. And then it finds, for example, a Spring XML file, find a bunch of annotations on a Spring class, because don't need that Spring anymore. It basically, oh, it's definitely Spring. So basically it downloads what you configured JVM version is. It downloads all dependencies, downloads the Spring, looks and say, oh, this application actually needs a connection to Postgres. Downloads the Postgres driver, builds everything you need to run as a container, so what I will call Droplet, and then orchestrates containers to handle that code immediately. That will work if it's a Java, that works with Python, that works with PHP, if it's .NET. We just have the stack that needs to run each kind of application. That's awesome from a user perspective, a developer, because I just don't care. I want to push it to the cloud and it works. It's great for operations because it saves a ton of time and useless work on basically taking a ticket and say, oh, deliver this VM. Oh, let me get this VM template here. And I'll deliver it back and I close the ticket. And then delivers to the next, maybe security guy, who actually lock that VM and see if all the ports are closed and everything's working fine. And then delivers to the guy that installs the application server, delivers to the guy who does that. So we automate all that to a point that you actually even get an automatic route out of your application, loads balance, everything. You kill a container, it restarts. You say scale, it duplicates those containers. So it's basically automation end-to-end from a developer perspective, doing all the heavy lifting. So basically you get the application, you push to the cloud, and that works. If you've never seen Cloud Foundry working, you're going to see some of that today as we were talking. It's going to be not necessarily only Cloud Foundry, but we understand how it works. Please.
When you talk about automating security, you just put that in there as a step.
Yes, there are several ways we handle security. One of them, for example, is we segregate where you deploy your applications in what we call organizations and spaces. They'll likely meet organizational structure and space for development. And what I can say is, for example, every single application, when I log into Cloud Foundry, you're going to see I'm going to choose an organization and a space. My organization might be, for example, innovation, which is a small org inside my IT group that's building new apps, for example. And my space might be development. And what I can specify is every single application that you push to organization, innovation, space development, that comes with IP tables a rule, for example, that close all the containers except accessing this specific database here on this port, etc. Other than that, you're all closed. It also will avoid any external access, for example. So you can configure that out in Cloud Foundry, have different rules for different spaces. Your source code doesn't change. Anything that doesn't change, you just push it to different places and it figures it out. We'll see some of that happen. And then once you're actually able to do that, we get companies that are working for us all the time You get, for one of the largest services in the world, Allstate working with us on doing that. We have Ford doing that with us. We have many others that basically what we have is they have a bunch of microservices that are deployed in Cloud Foundry that can basically deploy scaled across any cloud of your choice. It's an abstraction layer top of infrastructure APIs. And from that point, then I can actually go and say, hey, this application here, instead of 1, I want 5 containers running out of it. It scales immediately. You kill restars, then I can do hot deployment. I can, for example, upgrade an operating system or when Cloud Foundry is working on. Maybe there's a Linux fix for that security patch you want. And then you can update in real time without downtime. We do rolling upgrades. You can actually start doing all this automation in terms of microservices. But if you look at what we're actually getting when you just deploy a platform or a pass, we're basically getting an horizon of our legacy where you have a lot of basically separated but still kind of connected monoliths. We're basically refactoring one of those monoliths and actually creating a point of innovation inside your architecture, your enterprise architecture, that you can now start doing really fast coding, continuous delivery. However, you still have not only other systems to connect to and to bring to, most important than that, you gotta make those connections work and those integrations. And that's where we get the discussion from just microservices, which are stateless applications that rely on external services that I basically decouple on small services. I change this conversation how we really build enterprise systems that, as we call, have cloud-native capabilities. What we call cloud-native is exactly that ability of basically just writing the code that is business relevant to what you are trying to do. I don't need to write anything that is specific to that technology or to that infrastructure or to that cloud. I just push it, it just works. If I want to migrate from a different cloud because AWS is getting very expensive now, I want to migrate to Azure, I do that without changing my source code. I kill a container with stars. All those capabilities that you get on our platform, or what we call cloud native, you can actually bring this to make your enterprise architecture. And that's what we're actually focusing on, next step. Once you refactor this, how actually start to integrate the world. Does it make any sense? Yeah? Okay. What actually happens in most enterprises we talk to is actually, if you look at system A and system B here, those are traditional monoliths, which are currently connected to the external world because no system is an island, through integration bus ESB. How many of you used or use an ESB or integration bus? Okay. Those were amazing technologies for what we needed for that time, which was taking point-to-point integrations and actually getting all them into a bus that you can actually orchestrate those calls. The problem is this became the next monolith. And why is that? Have you ever tried to scale an ESB horizontally? If you haven't, you can try. I'll tell you it's not going to work. Those systems basically rely heavily on disk persistence. And if you need to spawn a new version, you actually need to share the disk. And then, of course, where the bottleneck is on the disk, right? It's like scaling a database. You have our Oracle rack. You can actually start up a new instance of Oracle rack. Are you scaling linearly? You're not. You add the new availability, you're scaling a bit, but you're not doubling the scale as you add the new version, you're not tripling it as you add the new one. You're really not scaling horizontally. And that means it's not bottleneck, and that's why people are deploying minimum data grids now. Because they basically don't want to buy new mainframes, which are like Exadatas, for example, which are just bigger boxes to make that work. That doesn't scale horizontally. The same happens with ESBs. People are putting so many integrations in front of that, that becomes the new bottlenecks. A lot of customers will complain that those are now the bottlenecks. They only deploy an expensive hardware. You can't scale them horizontally. And most important than that, as people start to experiment with more frequently deploying applications, especially on the edges where they connect, you need to change those flows internally because the data that is coming changed. And how do you change an ESB flow without redeploying the entire flow? How do you do that without impacting the other applications? And how do you do that in the middle of the day? That example that I gave about the security patch was actually a customer of ours who came and said, okay, my ESB obviously running on an operating system. And I wasn't able to upgrade this thing for a while because it needs to run constantly, because I have applications connected that are 24/7. But now I have an operating system that wasn't able to upgrade for a while, that is full of security patches, and now our security guys are like hammering me, what's the strategy for this? And there's no strategy. Day 2 operations. So,
I'm sorry, you're doing patch management. Like, you just take the typical OS, they find another bug in some sort of source code, they have to fix kernel code. How are you managing the patch process?
so imagine your platform is running on top of some system that runs on top of an operating system. Now we need to patch the operating system, right? Confounded, for example, on the way it's implemented, it's a set of microservices distributed over 30 microservices. Implemented, for example, if you want to deploy vSphere, those are VMs in vSphere. If you want to deploy AWS, they're also VMs. If you want to deploy bare metal, they're not going to be VMs, but whatever. Just like containers in general that can be physical or not. In Confounded, for example, when you want to do a system upgrade on an operating system, for example, we actually deploy another VM side by side with a new operating system version. We start to drain all that workload from the old VM towards this one. Once you're done, you shut it down. It's a basically rolling upgrade. And we do this across the entire system all the time. We have a cluster that if you want to have a first experience with Confounded, easiest way is go to run.pivotal.io. This is what we call Pivotal Web Services, or PWS. We were talking to a partner this afternoon, and I told them, they were blown away, that we have over 40,000 applications running Cloud Foundry here, and we have 4 people operating the system.
So
4, one at each 10,000 apps. Yes?
So your website or your servers is basically one big ESB, am I right?
No. But forget about the ASB. We get into that now, next. I was actually explaining how we upgrade the platform. I was talking about Cloud Foundry, which is a set of services that orchestrate application development, lifecycle, and deployment. That's not integration yet. Hold on. That's basically just a platform that allows you to basically push your app. So I'll give it a sense how that can be done internally, just to give an idea. When you push an application, you basically talk to what we call Cloud Controller. That receives the request, takes your binary, and runs to a component called Stager that figures out, is it a Java, is it a .NET, is it a Python, is it a PHP? Do I even know this step? Stages it, builds what we call a droplet, which is a container ready to run. Actually gets this and sends to the Cloud Controller database that is there. And once you have the deployment, then you can now orchestrate containers that are on the right there, those black boxes, all in one. Those are all separate components. And you can actually update the Cloud Controller, for example, without downtime, with all applications crashing, update the apps, update message bus, and everything works for us as a microservice. That's exactly what as microservices, of course. So I was saying that once you deploy, you actually have these capabilities, but you still have this old enterprise architecture scenario where you have those integrations made by a monolith as well. And most important than that, what do we usually do by the end of the day in those monolithic systems? Well, we transact with the data relational database. At the end of the day, we usually replicate that database to a different site or something for continuity. But much worse than that, we usually use an ETL, usually by the end of the day, to get all the transactional data that happened, crunch it, and send to an analytical database where you actually can run your analytical queries on. Anyone familiar with this? I've seen this before? Well, there are 2 big problems with that. First, you're going to be running your analytics based on yesterday's data because you're doing those batches overnight. Every single bank I talked to today, for example, they have their risk processes that, of course, are 40 years old in the mainframes and basically running analytics on analytical database based on batch processes. And how do we intend to do like Uber does today, that when you call an Uber, it tells you what the search price is immediately based on offer and demand. There's some really good analytics going there. There's some machine learning going out there. How do you actually do Airbnb, for example, that when you list your place, you have no clue how much you're going to ask for it, suggest you a fair price based on similar homes, what's the occupancy of the city at that point, is the holiday, is it? Calculates that at each 3 minutes. How do you want to deliver this kind of software if actually when you get an analytics, you get in yesterday? And more important than that, your systems are so separated that you can actually not feed the information back in real time. This is the kind of the next step problem that we actually touching at Pivotal. Our early journey, I would say, was taking customers that are building those monoliths, they didn't know how to scale those applications, how to deliver software faster, and tell a 100-year company like Ford, hey, you can do what Tesla is doing as well and develop software and make your car full of sensors, track the data out of the sensor, take decisions in real time, reroute as needed, do predictive maintenance. You can always do all those things together. You just need to have the right technology. You need to write software. You need to be a company that writes software as well. So we're taking those companies to deliver that. And the next step is, once the companies adopt, it will say they're into cloud native, how do you actually start doing continuous delivery in automated operations, not only for this siloed small applications that you built that is brand new, but how do you connect your legacy? How do you connect your data services, your backend services? And how do you make those real-time analytical cases work? That's the kind of problems we're touching today. Especially, not sure how many of you work here at ResMed. We have a very interesting cases with this in IoT or Internet of Things space, because we're going to be talking a lot about streaming data. And streaming data basically requires not only the ability to ingest data really fast from different sources declaratively, but to change that frequently, to actually make sure that process is something you always iterate on, especially if doing kind of data science work with that data, trying to figure out what to do with that data, because data science requires a lot of experiment. And more important than that, be able to deliver results faster to the applications we are on edge. So we are doing a lot of that. We started with a case with GE, for example, General Electric's, getting sensor data out of one of their turbines. There was a POC we did with them for a turbine that if I'm not wrong, runs on an energy thing. And be able to help them out and predict when they're getting close to a maintenance need based on the oil temperature, vibration of the engine, and other things you're getting. And it's all real-time streaming. So how do we fix this problem, and what's actually the cloud-native approach for what we call enterprise application integration, or system integration, right? We basically take a good look in what an integration pipeline is. And every time you actually getting data from system A to system B, or orchestrating different calls, and you can be orchestrating different microservice calls, you're basically talking about the integration pipeline. Integration pipeline is something that has a source, several steps of processing, and a destination. A source can be your sensor, for example, that is reading data from a medical device for the car, or a source can be an FTP server where Node system drops a file in that I ingest. From that point, you might do different processing steps with your data. You might, for example, parse that data, that if it's coming from a sensor, maybe it's a JSON already, and you want to do some parsing and figure out how it works or formatting it. If it's coming from a file, for example, you might want to convert from a CSV to something else. Maybe next step, you're going to be doing some filtering because you're not interested in all the data. Next processing step, you might actually, for example, invoke an external Spark cluster to do some computation. Whatever it makes sense to be your processing step. And at the end, you're going to put that data to rest either in a database or in a memory database, or deliver that back to a microservice directly. The problem is this thing as a whole is a monolith. I can't go back usually and say, Well, I want to iterate on actually deliver a new version, or actually add new capability, just for the data processing piece, which is step number 3. And by the way, that's really only where I need to scale. Because I read that file once from my FTP server, I don't want really many processes trying to grab that file at once, doesn't make sense. Once I parse it, it's a very lightweight process anyway. But now that I've split in different data feeds, now I want the maximum parallel to actually process data fast so I can actually deliver results faster. So we actually want these things to work as independent things. And what we're doing is basically taking every single step from the source to the destination and make it an independent microservice. So you can imagine an application, just imagine an app that you build. You don't have to build it. I'll explain how it works. But imagine that you build an application that all it does, it goes to that FTP server, for example, and grabs that file and brings it back. That's our first microservice, that's the source. If all that application does is that, and once it grabs the file, the return, it puts that on a messaging queue, then the next step of the process might be take whatever is on that messaging queue, ingest it, and parse it to a different format. Maybe output a JSON, and output JSON back to the other messaging queue. That the next step of processing will take it out, and will do something else, do the processing. And then if I want to scale only the processing part, instead of having one container listening to that queue that takes it from the parsing, I can have 3 or 4 and divide the workload between them. And now if you want to update one of those applications, you can just do what we call a rolling update. New version, take the route, because it load balancing, divide again, start draining from this, start putting some pressure on a new one. So do what we were rolling upgrade. If this application is down, the data is still on that queue, it's a messaging transport. Next one, we'll pick it up, we'll go for it. So we actually give that ability to have small applications that work the same. And for us, and if you use that, you know what it means. The smallest unit of a microservice, the easiest to build that you can do in 10 seconds, is basically a Spring Boot app, which is basically any application that you just do a tag and say this is a microservice, or this is a Spring Boot app. When you run it, it knows how to stand up, basically, listen to a port, direct a request to the right patterns that you configured. So now you can actually have small applications that actually work as a piece of a processing. And I'll explain what you need to do that. Any questions so far? Yes?
So you're saying that it's a shared network architecture, but the services obviously need to communicate with each other.
Absolutely.
And the way you're suggesting is that it automatically happens to queues. So as soon as you deploy a microservice into the cloud fabric platform, does the queue automatically become alive, or do you have to code for it?
I'll talk about that. Hold on 5 minutes, it will become very, very clear. So yes, you're totally right. And it's really good to stress that point. If you're actually building an application that will do that, or building a microservice that will do that, and from that point, as it carries a context, and it's not stateless, we call it a data microservice. If you really want to build that, you actually need to create that queue, connect to the queue, read that data, converting from the whatever messaging binary format the queue is on to whatever you want to transport as your data object, and work it out. When you return the right queue, and actually to somehow to inject that in your code. What's the configuration for, I don't know, the MQ series transport you're using, whatever. This is why we created what we call Spring Cloud Stream, which is the project that is the foundation of Data Microservices. And what Spring Cloud Stream is, and by the way, this was the new black for Spring 1. This is an ultra hot topic, Spring 1. We had 4 sessions, they are all packed, they all have a waiting list to get in. This is basically a Spring Boot app with a configured and in and out channel, and I'll show you, explain how it works. We're going to do it together. And the framework provides an abstraction layer where you can actually plug your transfer of choice. So let me explain it. You're going to take any Spring Boot application, and the Spring Boot application is just a method, a Java method, which is part of a class, and you say, this is a Spring Boot. And that method, it's used to be basically the main method, so it's like running a Java main class. But it basically runs in a container for you, opens a web server, listens to a port, connects a controller automatically. I'll show you an example of Spring Boot app. I can take any Spring Boot app that is made to run in any container, and I can say, now, all the parameters that come from this method are coming from my standard input queue. And everything I'm returning, I want to return to the output queue. I don't give it a name. I don't care what the name of the queue is. I don't care if I'm using RabbitMQ, if I'm using Kafka, if I'm using JMS, what the transport you want to use. I don't care what the name of the queue is. I don't care which cloud you're going to run it on. You basically only program the business logic of the method. And what actually happens is, when you deploy it to Cloud Foundry, to a cloud, it will basically automatically bind what we call a transport option or a service. It will be very clear when we do it, to those inputs and outputs. So that means Spring Cloud Stream will go there, and when you ask to deploy the Data Microservices, you will look and say, okay, it needs an in and an out channel. What do we have here available in this environment? Oh, there's a RabbitMQ service here. It will talk to RabbitMQ, create an in and an out channel for that. We will actually get the credentials, so username, password, IP, port. We'll inject all those credentials inside the container that is starting, so the container knows where it's connected to. There's absolutely nowhere you say this is a Cloud Foundry application that's done from Spring automatically. Then, basically, the framework knows how to connect it, creates the channels, connects it, and binds it that for you automatically. Actually, Cloud Foundry can do that for any applications, not Data Microservices. You can create an application and say, I'm depending on a Redis service, for example. We just use a Redis tag of Spring Framework. When you deploy to Cloud Foundry, it automatically binds, figures out how to connect to Redis, injects a credential, does that for you automatically. So you're basically using that for taking Spring Boot apps and automatically connecting to different transports.
So Fred, you are agnostic at the messaging
Layer.
mosquito.
And what's amazing with that is actually you can have a few environments in Cloud Foundry. And you can say my development environment is just running out on my laptop like this one. And I don't care about distributed testing. It's all I want to do is a functional testing. So for that, I'm going to run all in memory, and I'm using Redis as my transport layer. It's a Redis queue, basically. But if I'm deploying to my test environment and I don't touch the source code, exact same bits, deploy to development, it can use Rabbit to test. It might use RabbitMQ, for example, because that might be what's available in your test environment. And then when you deploy to production, maybe your standard in Kafka, you're going to deploy to Kafka and you don't change the source code. That's what the abstraction layer is. On the exact same way that I can have an environment that's running in AWS, an environment running in Google Compute Cloud, an environment running on OpenStack, and I don't change the source code, I deploy to each one of them, it just behaves exactly the same. And there's nothing in my application that says that this. It gets better than that. Because this is how it's supposed to work, just Spring Cloud Stream. There's no orchestration on how I create a flow and it deploys different microservices in order and connect them. This is just a single thing, a single microservice. This is how it works. Once you deploy those microservices in Cloud Foundry, they just become another application bound to a service in Cloud Foundry. That means that you not only you deploy in any environment you want, you scale with a click, you auto-bind to the services that are available to the marketplace, but you stream all the logs to the same location. So if I have an error, I don't need to SSH to those different machines and see where my logs is. They stream to the exact same location. Queue a container restarts, integrated metrics. So I can know, for example, my entire flow is taking currently 3 seconds to complete this data streaming flow. But I know how long it takes on every single component because I'm taking metrics for every single one separate, so I can know where my bottleneck is. So I can turn auto scaling on, and it's here automatically for me. I can do everything that is support from an application point of view in Cloud Foundry, so all what we call platform benefits apply here as well. So the things just become completely automatic. We're going to see it. We're going to see it work. I know it's a lot of stuff. And we're going to do some coding together anyway. I'll prefer to show this on the where you're actually looking at real source code. So I told you that for now, that was only the foundation of the microservices, the specific component, Spring Cloud Stream. But what we're talking about today is Spring Cloud Data Flow. And what Spring Cloud Data Flow is an automation for those data microservices. So what we're going to do together is actually create flows like this. I'm going to just, for example, information from an HTTP endpoint by listening for your device connecting and sending data from any sensor, for example. From that, I can apply a JSON filter because I'm only interested in some fields of all those. Then you can, for example, do a transformation with an external Spark cluster. And from there, you can split your pipelines. But what important is, once you hit deploy, Cloud Foundry will create a bunch of data microservices or deploy them, connect to the existing transport layer that you want, and it just works. And then from that, they're just another application. From that, for example, my enrich, I could be actually coding that again and deploying it again, and just do a blue-green deployment with the existing application that is running there. I don't touch the other ones. I can regroup them, I can change the flow, it redeploys only the deltas. So basically, it deploys cloud-native applications for data integration and system integration scenarios. Interesting things to note. First, I told you that you don't need to code all those apps. Why? I don't expect myself to write an application that connects to an FTP server and grabs a file and puts something else, like I said in my example. Because if I'm using this, I would expect this to already exist. It's a pretty common task. Somebody might have already created it, so I want to reuse it. Same would happen for any of this here. A filter, JSON filter. Dude, if you have 2 or 3 parameters, this should be pretty simple to be built, right? Really reusable. Or any process that we invoke external Spark process. Give me the name of the Spark process, I'll connect to a cluster and invoke it with what I have on the payload. So this should be all usable, and it is. So what happens is, when you deploy this, let's get back here. When you deploy a flow to Spring Cloud Data Flow, what it's going to do is, it's going to make available on your design palette existing microservices that are available on a central Maven repository that will make all the samples available. So you can grab an existing FTP server connection, for example, and a JSON parser, and a splitter, and a transformer, and I'll show you have dozens of options. But maybe one of those steps, and I think I did it that way, is a custom step. That custom means, of course, I need to actually have an easy way for you to bring your own application and make it a data microservice. So Spring Cloud Data Flow basically orchestrates the lifecycle of existing microservices that other people made available on a public repo or a private repo that you share inside your company, for example, and your own microservices that you bring, and orchestrate them as steps of a pipeline. That's what it does. How much time did we spend, like half an hour? Okay, let's take questions before we jump into code and example and live stuff.
Can you go back to the previous slide?
Yeah. Another one? Yeah. I think you wanted to see the abstraction layer. Is that true? Last slide. Last slide. This was the last slide, you mean? Yeah. It's going. It takes a while. I hate those animations, but people like it. Yep. Tell me.
So Kafka is transparent to the end user.
Let me get closer. Sorry. Go for it.
Is Kafka transparent to the end user of this client?
Absolutely. So what you're going to do, there is what we call a service API in Cloud Foundry. There are different ways of you do that. You can just call a provision method on a service that is exposed as the Cloud Foundry marketplace, like I would do here with Rabbit, and say, I want to provision a Rabbit instance. I want to use this free plan that gives me only 2 possible boxes, but I have no performance need, whatever. It's just a free plan. And you can provision a plan that knows exactly how to provision a cluster for you. So it's completely transparent for you. Or you can connect an existing Kafka cluster, for example, that is running your production. It just wants, say, Cloud Foundry. Whenever an application is to connect to it, there's the IP, the password, the port, for example, username. So you give the credentials. And then every application that you say bind to that Kafka cluster receives those credentials automatically when the container is created. And who is pushing the application, who is developing the application, has no clue. It just says, I need to connect to a transport layer called my transport. I have no clue what my transport is. So you basically work with basically names, like you do with an JNDI, an OJE in this, right? So you basically work on resource names, but they mostly relate to a service level agreement that you have on a service perspective in the platform.
Along those same lines, you were talking about having the credentials injected into the application.
Yep.
How does that relate to the publisher and the subscriber or the consumer configuration as well? Because you were saying it's a fairly dynamic pipeline as you can change it as part of the deployment process. Can you expand on that a little bit?
Yeah, well, basically what happens is, so once you connect, once you have a service registered in Cloud Foundry, and every single application that needs to bind or use that service, and that it's allowed to, you can say this is not allowed for those applications or those space. Any application that's allowed to, can actually say, when you push me, tell me that you need that service that's called my transfer, for example, and I'll connect to it. What happens is, those passwords, those credentials keep stored inside Cloud Foundry controller, and when it starts a container, it makes sure those are exposed as environment variables for the application. So every application, any single language that you can imagine can read an environment variable. So that's the 12-factor standard. So use the 12-factor standard to do it. Once you deploy those data microservices to Cloud Foundry, those are just apps. So that means, regardless if it's a source, a destination, or a transporter, what happens is it wakes up, it looks at the environment variables. There's an environment variable that string application will read. Say, for example, Cloud Foundry plus services dot my transfer, for example, knows how to connect to it. If you redeploy it, the new application gets the exact same credentials, unless you go to Cloud Foundry and say, no, new application will actually bind to this service instead, to this transport, and then it can rebound it.
Okay.
So it's very dynamic. It's very dynamic. And usually people who publish the application and people who actually create the services are usually different roles. One is more from operations perspective. The other one's more a developer that's just saying, push my application, I'm done with it. Maybe he has the credentials for dev, but he can't touch the services in prod. He can just connect to them because he knows the name. That's it. Yeah.
I have a question. So for your point, say for these 4 applications, so each of them connect to the same database. So in your view,
A database? No.
yeah, say, okay, for example, for simple example, each of the application, they have log information. So we have a central log, and this central log save all the log into the database, same database.
Logs we don't save to the database. What we do with logs, for example, in a platform, is actually we have a component collecting all the logs together. It is constantly rolling it up. And if you actually can connect to an external service like Logstash, for example, that they actually get streaming. They get streamed to Logstash. We don't store them.
Yeah, I guess what I'm saying is, of log just for example,
Okay.
I just say these four applications, microservice, they all write to the same database.
Not database, they write to a message queue
Oh,
that brings the information from one side to the other. Database is different. Database is not event oriented, right? The problem with,
but,
if they want to have the same context, they can write to the same data as well if you want to have some stateful context. You can also do that. That's really easy to do with Cloud Foundry. I'll show how to do that because one of mine does. But the minimum requirement is they need to share a transport layer. Forget about state. Imagine that you have an application and all it does is a calculator. I receive 2 parameters and a third is the operation. If I receive 1, 1, and plus, I'll return you 2. If I receive 1 and 1 and multiplier, I'll return you 1. This is a contract of the microservice, right? The only thing I need to do is actually connect the source of information to this call to a destination that will actually handle the next step. If your service needs to do something more complex, so let's say the 1, 1 and multiplier applies to a result they already had, so I need to have context. That's a stateful data microservice. You can actually, on the exact same way, make that application connect, for example, to external Gemfly or Redis and store that information and goes. It's supported as well. I'll show you an example of that.
yeah, but how can you say that? So my question is related. If they have the same database,
Okay.
they want to connect to. So it's what kind of
You might have a monolith.
design? Yeah, design for like we have a different design. Like say every service they just talk to the same database
So,
by their own for somehow. So another one is we can just put the database as one service.
so let me ask you a question. What are you gaining from doing that instead of doing a monolith? Because you're still putting all the dependencies on that database that everyone shares. That database still already becomes your bottleneck, right? All the dependencies are that can actually become your bottleneck. If you need to update that database, all the applications that depend on it are offline. You can have 20 applications all depending on the database. You have a central point of failure. Or you have at least a place that if you touch it, you might impact 20 different applications, right? So one of the things that when you're doing microservices, it's a very interesting concept, something that Martin Fowler came with a long time ago. It's called polyglot persistence. It's a usual thing. Of course, there are scenarios and scenarios, right? Usually, the best practice says that applications don't interact through databases. They interact over contracts or APIs. So I can have this microservice writing to Redis, this one writing to Oracle, and this requests information to this. Instead of writing to a database that the other reads, I make an API request. If you have all the services writing to the same data store, you almost building another monolith.
So you are talking. So you are saying for microservice, if any application
There are exceptions, sorry, yeah.
they have exceptions.
There are exceptions. Sometimes it's worth doing it. I need to change a lot of data. I don't want to talk about interfaces only because there's data in context. And maybe I have 2 microservices sharing the same in-memory data grid, for example, which can deliver events. It's not only request response. It's fine. But if you generalize that all your microservices write to the same place, yeah, you might be building another monolith. Just consider that. And we are happy. I'm happy to talk about that later on. They're really good. They're really good indications that you might be doing that or no in general.
You got 30 minutes.
Yeah, let's do like this. Let's go through. It's a very comprehensive demo. I'm sure you're gonna get a lot out of it. Let's go through that, and we're happy to get any questions in you all and after that. So this is a scenario we're proposing. It's a very complex integration scenario. We have an application that is an emulator for what we call point of sales. If you ever work with financial application, credit card, etc. So it's a POS. that's basically generating transactions randomly, like a point of sales, saying timestamp, transaction ID, account ID, value, and device ID. And device ID, I basically have one device for US county. You know, you understand why. So basically, I have an application that randomly says account 123, it's using device 23, which can be California, for example, can be my county, like Santa Clara in Mountain View. And that's generating a $102 transaction, for example. We have several of those to what we call a database. It's a scalable in-memory data grid. And then I have another application that whenever you transact, it knows that it has a device ID to a US county, so I show the transactions happening on a map. Super simple. Nothing fancy, no integration scenarios, just one app writing to a data grid, another one reading from it. Exactly the same what you described, right? But I want to go fancy. I want to be able to, in real time, evaluate a machine learning algorithm, and based on the machine learning evaluation, tell you how highly, how possible it is that you having a fraudulent transaction. So I'll basically give you a hint of possible frauds. And then you expect to see some transactions coming in green, for example, with some coming in red or orange. That's what you're supposed to do. So let's see how we can implement that without changes to the app. First thing I'm going to tell you is we're going to use pivotal exemplified as an in-memory data grid to transact those applications on. You could be using other in-memory data grid if you wish. It's just what I know how to use. But one very important detail is actually that Gemfire writes behind Greenplum all the transactions that are happening in real time. And Greenplum is an analytical database. So I have both of best of both worlds here. I have one layer at the top that can handle transactions really fast. So if you're ingesting data from, for example, a sensor, that's what GE used, for example, to get all the sensor data at once ingest into their data grid so it can actually take action upon it. But this writes behind a parallel database that you can run analytical queries. So instead of having that ETL that does it overnight, we basically write into a transactional database that is transacting to an analytical store. It has a mapping between regions and tables. It's really simple. And I'm going to start with that. Just simple. Let's use that as baseline. And then hopefully you're going to be amazed by a few things we're going to do. So I'm connected to my Cloud Foundry instance. And when you list the applications that are running Cloud Foundry, you have the name, what's their state, how many instances you have running, which memory is using, this, and then URL. Is what you get when you deploy an application, because you get a route automatically out of that. And one of these apps, that's right. One of these apps is just an application that I built that is listening to that information to actually plot some information. We're going to use this other one for the machine learning in a few minutes. Hold on that. So what I'm going to do right now, very simple, I'm just going to start a Spring Boot app. That's the emulator that is going to post those transactions to the grid, and we'll see them coming on the map. I'm not doing any machine learning yet. We will in a few minutes. Posting transactions. We see some green transactions coming, not red yet. I'm not doing anything fancy, just posting one and the other one's reading. Just make sure this is working fine. I'm going to stop the emulator right there, and we don't see any possible suspect transactions. Now what I'm going to do is I'm going to train an algorithm, a machine learning algorithm. If you don't understand how machine learning works, I'll give you a very quick hint about it, and you can research yourself about it later. And by the way, this is all an open source repository. I'm happy to share that with you later as well. And then somehow, we're going to take that insight as the transaction comes and decide if it's a fraud or not. So we start with deploying an application that I pre-deployed. I'll explain why. That's a clustering app. That's a machine learning that uses Spark, runs in Cloud Foundry, And what it does is make queries to Greenplan, so make queries to the data that it transacted before, in order to build this model. And this is the machine learning model. This is the exact representation of the model we built. I'm going to show you, it's a 20 line of code, it's really simple. So I'm taking from all the transactions that happened. So historically, I'm looking at an analytical database, historically. So while Jamfire is just storing what's happening in real time, I'm looking at historical data, I'm making queries to know from all transactions, where do they stand in terms of transaction value and the distance from home location. Home location for me, for example, it's Palo Alto, California. That's where I frequently transact. That means if I grab a flight now, go to China and spend $3,000 on a transaction there, will likely trigger a flag and say, oh, he's very far from home location and he's transacting a high value. Of course, real-world fraud detection systems use more variable than this. Those are just two common variables that I decided to use to make this easy an example. Once you make those queries, and if you're not into Spark or machine learning, the explanation is simple. Once you make those queries and figure out for each transaction what the value is and the distance is, you call an algorithm that is built, I did not program that, and you say, hey, train the model on it. And it comes with what we call 3 clusters. And one of these clusters has small and small values. So the small values on transaction close to home location. That means myself transacting at home $10. Nobody's going to flag that. To medium risk point, and to a point that the ones that we want to flag, those are high risk transactions. Far from home location, high value. I'll show you that once we train the model, and I pre-train the model because this has so much data, it's taking like 2 hours to train. But once we train the model, we come with what we call PML model, with an XML file that has this exact same information. I'm taking those 2 inputs, and I'm outputting either a low and low, a low and medium, or a high and high cluster. And these are the values of that cluster. Once you output this model, it's an XML representation. Any technology that supports machine learning can connect to that model and say, okay, tell me where I stand if I make a transaction that is $3 in New York. Now tell me where I stand if I make a transaction that is $9 in Europe. And then you get really quick answers. So once you trained the machine learning model, the evaluation is immediate. So what we're going to do is basically build a pipeline in Spring Cloud Data Flow that all data microservices that basically takes every single transaction from Jamfire, adds the distance from home location information to it, and from that I consume from a database. It's stateful. Needs to have context. So my POS, my point of sale, is not sending information saying how far from home location is, just saying I'm using this device, so I know where I am for the majority of the transactions. I know the distance. So I add that distance, I evaluate that machine learning model, and I receive as information back from the evaluation. Are you low, medium, or high risk? And then I'll apply a filter saying I'm really only interested on high risk transactions. And the results I'm going to ingest back to Jamfire in real time. This is why it's happening in real time. This is a real time what we call closed loop analytics or machine learning pipeline. Except the enrich phase, those are all reused microservices that exist and are shipped with the product Spring Cloud Data Flow out of the box. And then we're going to see that happen. So let's start with step 1. I'm going to deploy this machine learning application, confound exactly deployed. We could redeploy it actually, so you guys see it happening. Still have some time.
We have lots of time.
Do we? Okay.
9:30.
Awesome. So let's do something more fun.
I wouldn't train the system.
Nobody's going to wait for 1 hour, but Data Microservices, we can trigger a retrain. We don't need to wait for it to be done. So this is the application we're going to deploy. Sorry, I haven't opened it yet. Let's open my Eclipse or Spring Source Tool Suite. I'll show you a Spring Boot app. We're going to deploy that Spring Boot app in CF. Show you how it works. Let me close this here. So it's what we call clustering service application. As you see, it's an extremely simple application. This is the main class. You say, hey, this is a Spring Boot app. I don't need JBoss, I don't need Tomcat, I don't need any container to run this on. It stands up on its own. It embeds a container. It listens to a port. It does all the configuration by annotations. There's no XML to configure anything. So it's enabled configuration. It scans the components for annotations. It's a Spring Boot app, so I can run this right away, this main method that does all the injection for me of dependency, etc. And as requests come, it has a single controller. I don't handle servlets, of course, or any of that. It's just that as requests come, you're already listening to the port, standard ATP port. You're going to take all requests that come through /clustering, and I'm basically having two endpoints RESTful. One of them is a /train. That's going to call the method in Spark that I'm going to show you now that builds the model. Takes the result of the model as an XML, so it's a string. Saves this to Redis. Again, nowhere I'm saying that where's the Redis I'm connecting to. I'm just saying I depend on a Redis. This is auto-wired. When it deploys to Cloud Foundry, it finds the first Redis service available. And of course, I'm making it available for free. I'll show you how it binds. And it grabs and uses it. So there's no configuration here. Just say, I need a Redis. This is what you do with Redis. So it trains the model, gets the result, store in Redis. And as you hit this endpoint that asks for the model, it just pulls the latest trained model from Redis and shows you. That means I can keep training all the time, continuously, because I have more data coming. So it can retrain the model all the time with the new data, with the new fraud mechanism or new fraud standards that people might develop. So as you receive more transactions, you keep training at each 2 minutes, 3 minutes. And every time I hit this URL here, I'll get the last trained model that is on Redis. Simple as that. So just to give an example, let's start by, let me delete this app. I'm not deleting the data because the data is separate from the app. The data is actually at a Redis service that I provisioned here. And what happens is, when I push this application, I'm giving a manifest. I could pass those as parameters as well. I prefer to build a manifest. And I'm saying, I want this application to have this name. This is how much memory I want for each. This is how many instances I want. This is the host. Host is going to be the route. And it is going to add my domain, which in this case is local PCF dev.io. It's my local DNS. It's actually pushing this app here, and I'll give it the jar file. I could give the source code as well. Of course, it's going to take longer because it goes to compile first. I'll give the jar file. If I was using Spring Profiles, I could use Cloud. I'm not at the moment. And I need 2 services. If you try to push this application, you expect in your space in Cloud Foundry to have 2 services. One of them called Redis, and one of them called GPDB. What's GPDB? It's Greenplum. We're going to train the model in it. I'll show you. So I have no hard-coded user, password, IP, port, whatever. It's just provision here. This is the Redis. And once I hit train, I'm basically calling this, and if you've never seen, whoever uses Scala for anything. So it's the first time I'm going to see a Scala code. Spark, it's usually friends with Scala. We do a lot of Spark development in Scala. And it's a JVM language. So this is all it takes to train the model at this point. And you're going to see that I'm actually making SQL queries very complex with a lot of joins to Greenplum. And I'm basically figuring out the green plum URL automatically in Cloud Foundry. So what I do is I make queries in green plum. I figure out all transactions that happened. I sort them, of course, wherever, all the device locations, and then I figure out what the home locations are. So I make a query that looks everything that transact and where people mostly transact and order them. So customer 20 usually transact out of this county in New Jersey. Customer 21 usually transact out of this county in Denver, for example. And then for each transaction, I build a train set, and then for each